All right, question 20. The solubility of which of the following weak electrolytes would be most sensitive to a change in the pH of the solution? And to answer this, we kind of want to look at what are the ions in solution. So here I've got lead, I've got bromide, I guess I'll balance it, right? I've got iron, got cyanide, got silver, iodide, lead, chloride, and then silver and bromide. So we want to focus on the conjugate bases because conjugate bases, sometimes they behave like bases, right? I mean, we see something very similar about several of these right away. All right, bromide, iodide, chloride, bromide, those are all conjugate bases of strong acids. All right, so if we look at HCl, HCl is a strong base. It ionizes completely. There is no equilibrium. Because there's no equilibrium, that means that chloride is a conjugate base, but it does not behave like a base. There is no reverse reaction here. So that tells you any conjugate base of a strong acid will not behave like a base. It is not basic because it's the conjugate base of a strong acid. We know this because if you added like sodium chloride to solution, it would not change the pH of the solution because chloride, even though it's a conjugate base, does not behave like a base. The same thing would be true for iodide, bromide, nitrate. However, cyanide is related to hydrogen cyanide. Hydrogen cyanide is a weak acid. Because it's a weak acid, it's in equilibrium. Because there's an equilibrium, that means there's a back and forth. That means hydrogen cyanide will behave like an acid, it'll ionize, but that also means cyanide will behave like a base, pick up a proton, and revert back to hydrogen cyanide. So because cyanide is the weak base of a weak acid, it behaves like a base, right? There's this equilibrium. To have this reverse reaction, cyanide needs to behave like a base. So therefore, if I change the pH of this solution, if I make it more acidic, right? Well, it doesn't help us in this case. I guess I should have put it in this equilibrium up here. All right, if I make this more acidic, all right, if I protonate that, that'll take it out of this equilibrium and that'll allow more iron cyanide, iron 2 cyanide to go into solution. So this question usually gives people a really hard time, but it should be really easy because all we're looking for is, do I have the conjugate base of strong acids? If so, I can eliminate all of those choices. Anything that's related to a strong acid, eliminate that. What remains, that must be my ion, my conjugate base that's sensitive to changes in pH. There was a homework question that was very similar to this. I did a video on it. It was one of the videos I shared on the Blackboard announcement today as well. All right, question 21. What is the molar solubility of silver bromide given the KSP is 5 × 10⁻13? All right, we know AgBr is going to ionize and give us silver +1, bromide -1. So KSP equals my concentration of silver times my concentration of bromide. Right, we don't know silver. We can call it X. and it should be formed in a 1-to-1 ratio with bromide, so we'll call both of them X. So 5 times 10 to the minus 13 equals X times X. So X squared, 5 times 10 to the minus 13, square root of both sides, and X equals 7.1 times 10 to the minus 7. All right, what is X? X is my concentration of silver in solution. X is my concentration of bromide in solution. X is also my solubility of silver bromide. We talked about this in class, where people were getting hung up on this part right here. What is the molar solubility of? That's basically asking you how much silver bromide went into solution. It's the same answer as the X we're solving for, because the concentration of silver I have in solution came from the silver bromide. So my concentration of silver that I find in solution tells me that is exactly how much silver bromide could go into solution. So I know the wording throws people off, but it's the same question we've been answering, right? How much silver's in solution? That tells me how much silver bromide could go into solution. All right, what's the concentration of bromide in a saturated solution? So here it's just a little bit different, because we know lead 2 bromide is going to ionize and give us lead 2 plus and 2 bromides. And here, if we call lead X, we have to call bromide 2X, because we're going to get twice as much bromide out of that. KSP equals my concentration of lead times my concentration of bromide squared, because of that coefficient 2, right? I've had so many people ask, why do we have to use the 2 twice, right? We have to use it twice. We set it up once in the KSP, so I have to use the 2 here because that's the relationship, like that's the impact that concentration has on the KSP. The second place we have to use the 2 is in solving for X, because that's the relationship between lead and the bromide. For every 1 lead, I'm going to get 2 bromides. So if I call lead X, bromide has to be 2X. So we do need both of those 2's. All right, one accounts for the relative concentration between bromide and lead. The other one counts for the impact that bromide has on the KSP. So 6.6 times 10 to the minus 6 equals X times 2X squared, right? We multiply that, we get 4X squared. We multiply that by X, we get 4X cubed. 6.6 times 10 to the minus 6. All right, divide by 4. We get X cubed equals, so 6.6 times 10 to the minus 6. Divide that by 4. I get 1.65 times 10 to the minus 6. Cubic root of both sides, and X equals 1.18 times 10 to the minus 2. That is my concentration of lead. We were looking for the concentration of bromide. Bromide is 2X. So 2 times that should equal, right, 2.4 times 10 to the minus 2. or choice B for question 22. All right, question 23. We have a common ion. Question 24, common ion. And then 25, oh, was the pH one that we did in class. Yeah, we did 24 and 25 in class, actually. All right, question 23, the molar solubility of calcium fluoride, right? We should start the same way. Calcium fluoride ionizes, gives me calcium 2 plus 2 fluorides. And to that, I add sodium fluoride, the strong electrolyte, sodium fluoride. Ionizes, gives me sodium, gives me fluoride, right? And I have 0.05 molar sodium fluoride, which means I'm going to have 0.05 molar fluoride already in solution from my sodium fluoride. All right, our KSP, concentration of calcium times my concentration of fluoride squared. We know KSP, 3.5 times 10 to the minus 11. Okay, here it is a little bit different, right? I don't know my concentration of calcium, so we call that an X. I actually know a concentration of fluoride already. We're going to basically say that the concentration of fluoride from the strong electrolyte is greater than the concentration from the weak electrolyte, so we can ignore this concentration from the calcium fluoride and just say, all right, calcium is an X and fluoride is 0.05. We still have to square it because that's the impact that fluoride has on our KSP, but I don't need to double it. I don't need to worry about 2x because I have a strong electrolyte present. So I get 3.5 times 10 to the minus 11 equals 2.5 times 10 to the minus 3. Divide both sides by 2.5 times 10 to the minus 3. All right, 3.5 times 10 to the minus 11 divided by, I get 1.4 times 10 to the minus 8. That's my concentration of calcium in solution, and then therefore that's going to be my molar solubility of calcium fluoride, 1.4 times 10 to the minus 8. So hopefully that answered some of your questions. I think a few of you emailed me about kind of concepts like this of when do we ignore the 2? When do I have to double this, right? Here, this is the concentration of fluoride directly from sodium fluoride. So we don't have to double it. We know the concentration right away from sodium fluoride. I still need to square it, however, because I'm still plugging it into my KSP of calcium fluoride, right? That's where I want to know its impact on the solubility of calcium fluoride. Question 24 is going to be very similar. I think it's just a little bit different in what we're solving for. All right, we've got silver chromate. Ionizes. Right, my KSP, well, to that, right, I even tell you here, we add the strong electrolyte potassium chlorate or chromate. So potassium chromate ionizes completely. And I start off with 0.25 molar potassium chromate. Because it ionizes completely, 0.25 molar potassium, actually twice as much potassium because of that coefficient 2, and 0.25 molar chromate. All right, KSP equals concentration of silver squared times the concentration of chromate. My KSP is 9 times 10 to the minus 12. Here again, it's a little bit different, it's a little bit, you know, but like a nuance of how and when to do things like this. So here, if I did not know either of these concentrations, I would say 2x and x, and I would get the 4x cubed, and I would go that whole route. Here, however, we know one concentration already. We know the chromate from the potassium chromate. So we're all set with chromate. I don't know the silver's concentration. But because it is the only unknown in this case, right? We're not solving for anything else. We're just solving for silver. So I can say silver is X. That's the only unknown we have. Still has to be squared because it's in the KSP expression we just wrote, times my concentration of the chromate, 0.25. So divide by 0.25 on both sides. I get x squared equals, so let's see. Divided by 0.25. All right, 3.6 times 10 to the minus 11 square root of that. All right, I asked you to ask questions so everyone can see, because all of you just asked the same question, all right? So after explaining, right, it is not 2x because we would call it 2x if I did not know either of these concentrations, right? If both of those concentrations, if both of these concentrations were unknown, I would say this is x and this is 2x. But in this case, I don't have two unknowns. We just have one unknown. Silver is my only unknown because it's the only thing I'm solving for. We can just define it as x. We don't need to define it as 2x because it's the only thing we're looking for. So we have chromate concentration, so we can just say silver is my x. And then, correct. So the next question was, what do you do at the end if you put it as 2x? If you put it as 2x, the last thing you'd have to do is just to multiply this by 2, right? To get you to the actual concentration you're looking for.
Wait, why wouldn't you multiply it by 2 after you found that concentration? Because the coefficient in front of AG is 2AG.
Yeah, so we don't need to multiply it by 2 because we defined it as x. So as soon as we find x, that is actually the concentration of silver already. As Ariel is saying, if we defined it as 2x, then you'd have to multiply it by 2 once you actually found x. Here, we don't have to multiply it by 2 because we're saying the silver concentration, whatever it is x. So it's already kind of taken into consideration right? That coefficient of 2 is there, because we're looking for what is all of the silver concentration, and we're just calling that our unknown X. If that answers your question, Lily.
Yeah, thank you.
Yeah, Audrey, I think it's, I mean, I don't know, I'd have to look and see. I mean, it's a little bit, probably more than half or close to half. All right, and then question 25, we did this in class on Thursday as well, right? What is the pH of a saturated solution of manganese hydroxide, given the KSP of manganese hydroxide is 2 times 10 to the minus 13? I thought it was a good review question because it kind of brings together our solubility, and it brings together our pH questions, right? So manganese hydroxide ionizes, gives me manganese 2 plus 2 hydroxides. And we know KSP equals the concentration of manganese, the concentration of hydroxide squared. Now to set this up, right? So here we don't have any common ions. So here we have 2 unknowns, the manganese concentration and my hydroxide concentration. So manganese is X, hydroxide is 2X. So we'll plug into our KSP, 2 times 10 to the minus 13 equals my concentration of manganese, my concentration of hydroxide. All right, so we are in the 4x cubed pathway. All right, divide both sides by 4. I get x cubed equals divide that by 4. 5 times 10 to the minus 14 cubic root, so second. All right, I get x equals 3.68 times 10 to the minus 5. This is where this one gets a little bit harder, is because we called manganese. So here we have to multiply by 2 because we called manganese X, we called hydroxide 2X. So that's my manganese concentration. We need pH, right? We can get pH from POH, and then we can get POH from my hydroxide concentration. So I need my hydroxide concentration. So 2x equals 2 times 3.68 times 10 to the minus 5. So 7.37 times 10 to the minus 5 molar is my hydroxide. Exactly, right? That's how we're solving this, is we're defining it relative to something else. And that's why we need the 2x there. Because if we have 2 unknowns, we're saying, okay, one of them is x, and then one of them is a multiple of that. Most often, 2x, but it could be 3x, right? If it was like the lanthanum fluoride or something that I gave you on the exam, right? Like this one right here, right? If we were to solve this one would be x, and that would be 3x, for example, because that's their relative concentration. But back to this question, right? POH, negative log of my hydroxide concentration. POH equals negative log of 7.37 times 10 to the minus 5. 4.13, and then the last step, pH plus POH equals 14. pH equals 14 minus 4.13. So my pH equals 9.87. All right.